Morning, guys. Okay, so it's already 10 and we should get started. Okay. So this class, we're going to start a little bit about the VOC control. So as I said, VOC is a very large group of pollutants, right? It's not a single species, and there isn't a universal method to remove all of them. So that's why there are actually quite many methods that we're going to go through for the next few classes. So if we do a quick recap of our last class. So last class, we mainly worked on the carbon dioxide sequestration and a little bit properties about the VOC, right? So we said that for the carbon dioxide sequestration, it's a very important part in the process of controlling the carbon dioxide. And it's one thing to capture the carbon dioxide, but it's another thing to store or to just basically to put them to the ground or to the ocean, right? And there can be quite a lot of challenges to do that. So then we talk about the VOC species. So first, we try to differentiate the gas or vapors, and we realize that we call them vapors because they have a boiling temperature that is quite close to our quite close to the temperature that we're dealing with every day, right? And then we introduce the properties of these vapors. So we said that the vapor pressure basically is the maximum pressure that a species can have in the air, right? So basically it's under equilibrium, right? And there is a equal flux from the liquid to the gas phase and from the gas phase to the liquid phase. And then we also said that the equilibrium is going to take forever to achieve, right? So that's why in most of the scenario, because we have a relatively shorter time for the contact of air and liquid, so the pressure of this species is not going to reach to the vapor pressure. And that's why we created a term called the partial pressure, right? If we use the symbols to show them, then that they're going to be PVI or and PI, right? And we said that actually the RH, the relative humidity, is defined as the ratio between the partial pressure and the vapor pressure. So we never see RH larger than 1, right? If you check your weather app, right? Typically, even if it's raining, it's going to show you an RH of 100%, never above 100%, right? So which basically means that in the system, the partial pressure has to be always smaller or equal to the vapor pressure, larger or equal than 0, right? It cannot be a negative pressure. So this will constrain the partial pressure of the species in the air. And we also said that not only this partial pressure can change, the vapor pressure can also change. And it's actually a strong function of temperature, right? We said that for water, at least for water at 100 Celsius, the vapor pressure is 1 atmosphere. And at 25 Celsius, this vapor pressure is 0.03 atmosphere. So there's a very significant change as a function of temperature. And we said that we could use the equation, which is called the Antoine's equation, to describe this change as a function of temperature. So I'm listing this equation here again, right? So in your textbook, although it says that these A, B, C values are constant, but generally the B value, on the textbook, you have the equation of A plus B divided by C plus T, okay? But in general, this B term here is always smaller than 0. It's always negative. So that's why people would prefer this equation to describe the Antoine equation, right? So in this way, A, B, and C values are all positive. You don't need to worry about which either negative or positive values these parameters take, okay? And then here is a table. I think I showed this briefly last class. Here's a table showing the ABC values for water, right? You can see that all of these are positive. And if you recall, so basically, if we show everything in the linear scale, you can see that the vapor pressure increased almost exponentially as a function of temperature, at least for water, right? And this actually works for all the vapor species, all the gas species. And we also show that in your textbook, there's a table or there's a figure showing the vapor pressure as a function of temperature, right? Probably in last class, the projector wasn't having a very high resolution, but if you see here, each line is basically showing a specific VOC, volatile organic compound, okay? You could have butane, you could have hexene, benzene, and so on. Excuse me. So basically, this is showing how the vapor pressure change as a function of temperature. And since we're showing the y-axis in the log scale, right? Since we're showing in the log scale, so the curve is not like this anymore, right? And also, we're showing the temperature in a different scale as well, right? This is not log scale either, right? And then in this way, we can better manage the curve so that they're on straight lines. So it's much easier to deal with the straight lines. We could do the interpolation and so on. Okay, so this is what we talked about in our last class. And in this class, we can continue this discussion and also introduce a method actually to remove the VOC by using the vapor pressure. Okay, so well, we said that generally the RH value is always smaller or equal to 100%, larger or equal than 0, right? So what's going to happen if the RH is larger than 1? Okay, are there going to be scenarios where the vapor pressure of the water is much higher than the partial pressure? Actually, there are a lot of these scenarios. So if you think back, when we talked about the particulate matter, we mentioned the condensation, right? So during the winter time, we could have the breath fog, right? So basically, that is due to this this RH value larger than 1, because what really happens is that, let's say in the body, our temperature is much larger than the ambient temperature during the winter time, right? And because of that, the air that we exhale out is also going to have a higher temperature. So what that means is that basically the PVI in the body is going to be larger than the PVI in the ambient. So if you just consider this temperature difference, right? And also because the air, when we inhale them from the ambient and then exhale them to the outside, so basically it's picking up the water vapor, right? If you consider the partial pressure now, so it's picking up the water vapor from our body. And because we have a higher temperature, right, it's going to be able to pick up more water vapor. So basically you're going to have a PI value, right? The partial pressure of water in the body is also going to be relatively high. And because of that, it's also going to be higher than the PVI in the ambient. So what it means is that when we exhale the air out, the partial pressure water vapor is going to be higher than the saturation vapor pressure in the ambient. And due to that effect, if you consider the relative humidity of the exhaled air, right, that's PVI divided by PI divided by PVI ambient, that's going to be larger than 1, okay? And because of that, we said that the water vapor is going to condense onto the existing particles and to form the fog, right? And this is a condensation, and we're actually using condensation in a lot of places. We said that the clouds are actually formed because of condensation. The reason is, let's say this is our ground, right? So our ground is generally more humid because we have a lot of water bodies, right? And also the temperature at the ground is going to be higher compared to the temperature at higher altitude, right? Let's say that this is TC is a cloud. It's a cloud level, and TG is a ground level. Okay, so because the TG is higher than TC, right? We also have the relationship that the PVI at the ground is going to be higher than the PVI at the cloud level, right? This is talking about the vapor pressure or the saturation vapor pressure, right? We also said that because the ground also has more water body, so because of that, if you consider the partial pressure of the water vapor, it's actually also going to be higher than the vapor pressure at the cloud level. Okay, so now if you imagine, let's say that this parcel or this box of air start to rise up. So as it rise up, till its vapor pressure reach to the same value as the partial pressure, same value as the vapor pressure in the cloud level. While at the same time, the partial pressure of water vapor didn't change at all. So whatever is at the ground is the same at a higher altitude, right? So in that scenario, right, then you basically at the cloud level, PI divided by PVI cloud is going to be larger than 1. And that's why these water vapor is going to condense onto the existing particles, right, to form the clouds. Okay, so this is also how the cloud are being formed because of this condensation effect. So here I'm also going to show you a pretty interesting video to show how to make the cloud at home, actually. Okay, so what we need is just a bottle, right? A plastic bottle, like a soda bottle, right? And then you could find an air pump and start to pump in air. What you should also do is that you could add some liquid inside, either water or some alcohol, right? And see how we can do that.
So our valve stem goes up here. We're going to do the same as before. We're going to increase the pressure. And then as soon as we release the pressure, those molecules are going to go from a high state of energy to a lower state of energy. Anything that's evaporated will condense, and that's where we're going to get the cloud. So watch how different the effect is here. So again, I'm going to watch it carefully, make sure I'm not putting more than about 20 pounds of pressure in there. Oh, did you hear it? So you can start to hear it kind of pushing out. All right, here we go. I think that's probably pretty good. Watch this. 3, 2, 1, bam, and there's your cloud. Now watch, I'm going to cap it back off again. So I've trapped the cloud in here, and now I'm going to continue to add pressure. Really kind of simulates the burn off of fog in the morning. Watch this. As we increase that pressure, look, fog starts to disappear. Cloud vanishes. Very cool. Look at this. So now we are back to the process again. Here we go. 3, 2, 1, bam. And and there's our cloud. So if you've ever done a soda bottle rocket, many times you'll see that bottle in the
Okay, so this is a simple process to actually make a cloud at home. Okay, so we can actually discuss what is really happening here. Okay, yeah, so as the video shows, right, we could just use an air pump and a water bottle, right, to make this effect, right? So if you think about the air that's being added into the bottle, right? So basically we're increasing the pressure in the system, right? And what we're also doing is, if you consider the air and the water bottle as an entire system, right? What we're doing is we're adding work to the system. We're doing work to the system, right? So according to the thermodynamics law, if you do the work, right, it's going to rise up the temperature, because basically you're adding more energy to the system, right? So if the temperature increases, then what's going to change? So the vapor pressure is going to change according to the Antoine's equation, right? The higher the temperature, the higher the vapor pressure. So basically, you're creating a scenario where you're increasing the vapor pressure, increasing the total amount of allowable water vapor in the system, right? So if you write out the equation of RH, right, the relative humidity is equal to Pi divided by PVI, right? So basically, you're increasing this term. This is going to make the RH decrease. So if the RH decreases, then what's going to happen is more of the water vapor, or more of the water in the liquid, is going to try to escape from the liquid phase, because RH is lower, right? So you create an imbalance here. So which means that there are less water vapor, right? So more of the water tries to escape from the system, right, to get into the air. And because of that, the Pi will also increase, right? So basically, when you are adding pressure into the system, what happens is that you're creating a scenario where the RH decreases, you're promoting more evaporation, right? So more of the water is going to evaporate into the gas phase, right? And now let's think about what's happening when we open the seal here, when we open the cap, right? You can hear the burst. So the burst happens because the entire system that's sealed in the bottle actually does work to the outside, right? It does work to the outside. So according to the thermodynamics law, right, if you do work to the outside, then the temperature is going to decrease, right? If temperature decrease, then the vapor pressure decrease, again, according to this Antoine's equation. So now if you write out the RH equation again, Pi equal to PVI, now you have a smaller value of the vapor pressure, right? So this actually the vapor pressure responds very fast to the temperature, while at the same time, the partial pressure, the existing water vapor cannot respond that fast, right? If that cannot respond that fast, then you create the condition of RH larger than 1. If the RH is larger than 1, you have condensation, and that's why you form those clouds in the bottom. Okay, so this is how you can create a bottle. But if you think about the second part of this video, right? If we start to pump in air again, so what's the reason why the cloud vanish? If you go back to the beginning, you increase the pressure, you add work, right? Temperature increase, PVI increase, and actually that promote evaporation. So that's why those cloud droplets evaporated, and this is because you're increasing temperature in the bottle, right? And you're affecting the RH, and that's why those water droplets just evaporated. Okay, so this is a simple process to use, let's say, the vapor pressure or the partial pressure to create clouds or to create this condensation effect, right? And actually in air pollution or the air pollution control, we can apply this method quite easily. So if you think about trying to remove some vapor from a gas stream, let's say that we have a duct, right? And the duct has quite a lot of pollutants inside, especially the VOC. So the VOCs, if they are in the vapor form, right, then we said that it's very difficult to tell from the gas phase molecules. Let's say you could have some benzene, right, or formaldehyde. Let's say we just use F to show them formaldehyde. And then at the same time, you have oxygen or nitrogen. And when they're in the vapor form, it's very difficult to remove them because they are single molecules and you don't have a sieve or something to get them out of the gas stream, right? And in that scenario, if we can create this condition where we can condense all of these VOCs, we said that oxygen and nitrogen, they're gas, right? They're not VOCs, mainly because their boiling temperature is much, much lower. So if you decrease the temperature, these molecules are not going to condense, but the VOCs are going to condense, right? If they condense to form a cloud, form particulate matter, right? It's much easier to remove particulate matter than to remove the air molecules inside. Okay, so this is going to be the first method, our first method to remove the VOCs. That is to use the condensation to get rid of the VOC. Okay, so here I have a question or example problem where we can take a look, right? So we can see how we could use this condensation method to remove some VOCs from the gas stream. So let's see that, see this problem here. So it says that an airstream is presently at 1 atmosphere. So we know its pressure, it's just at ambient pressure, and at 160 Fahrenheit. So this is around 71 Celsius. This is pretty warm, right? But not very hot because at this temperature, the water vapor already condensed, right? And it also contains 40,000 ppm of toluene. So we're trying to remove the toluene out of this gas stream here. So it's asking to what temperature must the air be cooled to remove 2/3 of the toluene vapor, right? So it says that we have to reduce the temperature. So the reason behind that is in order to remove these VOCs through condensation, we have to create the scenario where the PI is larger than PVI, right? If PI is larger than PVI, if you think back for the water case, right, PI divided by PVI, right? If it's larger than 1, it means that water vapor can condense. So it's the same for the VOC. We have to create the condition where the PI is larger than PVI. So we can't do too much things about the partial pressure. So that's why we have to reduce the temperature to reduce the vapor pressure from the system, right? So then let's see how we can work on that. So we have to go back to the curve or the figure that the textbook has, right? So in this figure, it's basically showing what's the vapor pressure of all of these organic species, the VOCs, as a function of temperature. So if you zoom into each line, right, you can see that the toluene is actually this line here. So I'm labeling that with the red color, okay? So toluene is right here. And again, if you look at the trend of this curve, so the vapor pressure, the PVI, is going to increase as a function of temperature. So that's why when you cool the airstream down, basically the vapor pressure decreases. And that's the reason why you create the condensation to remove these VOCs, okay? So if you look at this curve here further, it's actually showing the pressure as with the unit of PSI. But here, if you look at the problem, it's showing it's just showing you the molar ratio, right? Not the pressure value. So we have to find a way to convert the molar ratio into the partial pressure, okay? So according to the ideal gas law, right? So we said the molar ratio is defined as this. So whenever we talk about the ppm or ppb, ppt, that's just the number of mole divided by the total number of mole in the gas stream, right? So according to the ideal gas law, so actually the molar ratio is exactly the ratio between the partial pressure and the total pressure. Okay, so I'm not sure if you have heard of the term of partial volume, right? So the partial volume is defined as VA divided by V. So basically, the molar ratio also describes what is a pressure ratio and what is a volume ratio. Okay, so here we're trying to find out what is the partial pressure of the toluene. So we could just use this part of the equation, right? So basically we have PA, or let's say P toluene, divided by the total pressure is going to be equal to N toluene divided by N total, right? The total number of moles. And here we have this ratio here equal to 40,000 ppm, which is equal to basically 40,000 multiplied by 10 to the negative 6, right? And that is equal to 0.04. Okay, so what this means is that the toluene, the partial pressure of the toluene is going to be 0.04 atmosphere. Okay, so any questions until now? Am I going too fast? All right, so if you have any questions, you could put in the chat or just unmute yourself. All right. Okay, so let's see here. All right, so if you look at this curve again, it's having the unit of PSI, right? It's pounds per square inch, right? And here we have the unit of atmosphere. So we have to convert this unit. And we know that 1 atmosphere is equal to 14.7 PSI. So basically, if you plug in this unit conversion here, you could have the partial pressure of toluene equal to 0.04 multiplied by 14.7. That is equal to 0.588 psi. Okay, so this is basically the partial pressure of toluene at the temperature of 160 Fahrenheit. Okay, so now let's see where we're at for this on this curve. Okay, so we said that this curve we just show here, this is the vapor pressure curve, right? And then if you plot out the point, right, we were at 160 Fahrenheit and the partial pressure is 0.588 psi, and the temperature is 160 Fahrenheit. Okay, so now let's draw a point on this curve, right? 160 is somewhere here. Okay, and then if you look at the pressure, it's using PSI, 0.566, that's 588, that's close to 0.6, right? So we're at somewhere here. Okay, so you see that this point is below this curve, below the curve for the toluene, and that makes sense because we know that the partial pressure cannot be higher than the vapor pressure of the toluene. If it's higher than vapor pressure, then it's automatically going to condense, right? And now let's see what's going to happen if we cool down the system, right? If it cools down, basically it means that the temperature is going to move towards the left, right? And it's going to go towards this direction. Okay, if I draw a straight line. Okay, it's going to move towards this direction. Okay, and if we, let's say, at the beginning of the cooling process, okay, the toluene is not going to condense at all. Let's say if it just cools down for until around 100 Fahrenheit, right? The toluene is not going to condense because its vapor pressure is still lower than because its partial pressure is still lower than its vapor pressure. Okay, so basically the toluene is still going to keep its vapor form and flow happily in the gas stream until it hit to the point of the vapor pressure, until it hits to this point. Okay, so what's going to happen next if we further cool down the temperature? So can the toluene vapor pressure come to this point? It cannot, right? If it's higher than this, if it's at this point, it means that the partial pressure is higher than its vapor pressure. It's going to condense, right? So it's going to automatically reduce the pressure to follow this line here. So basically, what happens is that once it hits to this line, it's going to follow this line. It's going to follow this vapor pressure line, right? Until to the temperature where we remove 2/3 of its original amount of toluene. Okay, so if you look back on this problem, so it's asking what is the temperature that the toluene, basically we can remove 2/3 of the toluene vapor. So if we remove 2/3 of the toluene vapor, what that means is that the partial pressure, let's say cooled, under the cooled condition, is just going to be 1/3 of its original partial pressure. Okay, so that's 1/3 multiplied by 0.588. Right? So that is going to be 0.196 psi. So we have to find the temperature where the vapor pressure of the toluene is 0.198. Right? So basically after the cooling process, the new pressure of this toluene is 0.196. So that is close to 0.2. Right? So basically the goal that we have right now is to find the point where the vapor pressure is 0.2 psi, and you can see that the point is right here. Okay, so this is 0.2, right, or close to 0.196, right, and then the temperature is basically between, let's say, 45 and 50. Okay, so this is how we can use this vapor pressure curve here to find the temperature where we can remove certain amount of VOC. All right, so if you think back on this process, right, so let me remove all of those drawings on here. So what happened is we can first find out what is the state of these VOCs, right? We said that the original partial pressure is 0.588 psi, right? It's had a temperature of 160 Fahrenheit. So we find this temperature, we find a point where it has the original partial pressure, right? That is close to 0.6, is somewhere here, right? We can plot that data point. And then as we cool down the temperature, the system is going to follow this straight line to the left, right? Until it hit this vapor pressure line. And we know that the system cannot go across this line here, because if it go across, then basically the partial pressure is higher than the vapor pressure, the condensation happens. If the condensation happens, the vapor pressure is going to, the partial pressure is going to decrease, right? It's automatically going to change this point back to this line here, right? So we find our final goal. Our final goal is to maintain the partial pressure at 1/3 of its original vapor pressure, which is 0.2. We find this point here, right? And then you just find the temperature that corresponds to this point. And that is the temperature you need to cool down the system. Any questions for this process? All right. So well, you also have a one or two homework problems to let you practice with this condensation problem. Okay. So if you think back on this condensation method, I would make an analogy to the gravitational settler. Okay. So if you think what's happening in the flue gas, right? So we know that when we emit the flue gas from either coal-fired power plant or from any industry, right? Typically, the flue gas temperature when it first enters the duct, temperature is very high, right? And as it flows through the duct, the temperature is going to automatically decrease because there's heat exchange to the with the ambient, right? So actually, you don't have to create some refrigeration condition to cool down the flue gas. What you can also do is you just leave the duct like that. And then the temperature is going to automatically decrease, right? If the temperature decreases, the VOC condense, and you can get rid of those VOC. So it's very similar to the gravitational settler as we introduced earlier, right? The gravitational settler, for those, we don't create a chamber to remove the particles. What happens is that these particles are going to automatically settle down by itself in the duct, right? So everything happens by by this natural process. So we don't have to create the condition where we either lower down the temperature or we promote the gravitational settling. So I would say this condensation method is very similar to the gravitational settler, right? So both of them are a passive method. So it just happened by itself. We don't need to do more controls on it, right? And because of that, this condensation removal is not going to be very efficient, right? And excuse me. So as you can see, we can only remove, let's say 2/3. We cannot achieve like a 99% removal efficiency for the VOC. So that's why we have to think about some other method, right? So there are actually a series of other active control method to remove the VOC. So you can remove them by liquid, you can remove them by solid. Okay, so if you're using these more active method to remove the VOC, then there are generally two processes involved. So one is called the absorption, okay, and the other is called the adsorption, okay. So you can see the major difference here. So one is B, one is D here. But what really happens is how we're removing these VOCs. So here I have two schematic diagrams to show you this process here. So when we talk about the absorption, what happens is that the molecules can actually penetrate into the body of the liquid, okay? So what's occurring is that molecules are drawn into the bulk of the phase. So if you consider that we have a bottle of water, right? And then at the same time, you have sulfur dioxide in the gas. So the sulfur dioxide molecules can actually penetrate all the way into the body of the liquid. Okay, so this is what's called the absorption. In terms of the adsorption, right? So what's occurring is that the molecules are just adhering to the surface of the phase. Okay, so this is more general when we're talking about the solid. We're trying to remove some vapors with the solid. Okay, so one perfect example is the activated carbon. So I think I talked a little bit in the NOx control that we can introduce those activated carbon into the system, right? So the activated carbon has a very rough surface. Okay, so what it means is that it has a very high surface area. So if it has a high surface area, then more of the molecules can actually attach to the surface of this solid here, right? So in this way, you can remove the gas from, remove the VOCs from the gas phase. Okay, so we can start from the absorption first, right? So I would say that the amount of the VOC that can be removed by absorption is regulated by basically a equation, which we call the Henry's law, okay? So the Henry's law determines what is the maximum amount of the VOCs a liquid system can absorb. So basically, what's happening is that you have the vapor pressure of the species, right? It's going to be equal to a constant multiplied by its molar ratio in the liquid phase. Okay. So this is the Henry's law, right? As I said, the partial pressure is going to be equal to a constant multiplied by the molar ratio or the molar fraction of the solute in the liquid phase, or more simply speaking, that's the mole fraction. Okay. So I think a simple example can be, let's say that we have a bottle of water, right? And then there is sulfur dioxide in the water. Okay. So what's going to happen is that the sulfur dioxide and also the sulfur dioxide are actually trying to escape from the liquid form, okay? And there's also going to be sulfur dioxide in the gas phase. So basically you have a balance of this system, okay? We're reaching to equilibrium, right? And under equilibrium condition, the partial pressure of the sulfur dioxide in the gas phase is going to be equal to a constant multiplied by the molar ratio of the sulfur dioxide in the water. Okay, so they're going to be linearly correlated with each other. For example, let's say that you have 1% of the sulfur dioxide in the gas phase, right? It's going to achieve certain equilibrium here. And for example, you with that, you achieve a molar ratio of 1 ppm of the sulfur dioxide in the liquid. Then if you increase this partial pressure, or if you increase this percentage of sulfur dioxide to 2%, basically you double the amount of sulfur dioxide in the gas, right? And then what's going to happen is that in the liquid, the sulfur dioxide concentration or the molar ratio is going to automatically change to 2 ppm. So you have this linear correlation here. Okay, so what will determine this constant, or what will determine this linear interpolation? So that's this constant here. And this constant here is called the Henry's loss constant. Okay, so basically, if you know what is the molar ratio, you can just multiply that with this constant to find what is the partial pressure. All right, so this table here shows you all the Henry's loss constant, right? For example, you can have carbon dioxide, carbon monoxide, let's say hydrogen sulfide, so on and so forth. But one thing to pay attention, that we should pay attention, is this exact value. Okay, so you can see that to show these value here, the Henry's loss constant is multiplying 10 to the negative 4. Okay. Let's say that for carbon monoxide, okay, at 30 Celsius, the carbon monoxide has a Henry's loss constant in the table of 6.2. So what it really means is that the Henry's constant of carbon monoxide basically multiplied by 10 to the negative 4 is 6.2, okay? So the actual Henry's constant for carbon monoxide is 6.2 multiplied by 10 to the 4th, right? And it's going to have a unit of atmosphere per mole fraction. So we could do a simple practice with this example problem here. So if you look at this problem, it's trying to ask us, what is the equilibrium partial pressure of the carbon monoxide in the air that is in contact at 20 Celsius that has 1 multiplied by 10 to the negative 6 mole fraction of carbon monoxide. So this is indeed talking about carbon monoxide system, right? So we know that we have to focus on this column here. And you have a temperature of 20 Celsius, right? So under this situation, the Henry's constant basically multiplied by 10 to the negative 4 is 5.36, right? The Henry's loss constant is 5.36 multiplied by 10 to the 4th. And that unit is atmosphere per mole fraction. Okay. So it is asking for what is the partial pressure. So basically the partial pressure is equal to HA multiplied by the XA, right? And we already have the HA equal to 5.36 multiplied by 10 to the 4th. And the XA here is the mole fraction, right? That is 1 multiplied by 10 to the negative 6. Okay. So with that, you have 5.36 multiplied by 10 to the negative 2 atmosphere. Okay, so as simple as that. So with this Henry's law here, basically you can see that if you want to absorb any VOCs or any gas, right, there's always going to be a constant that determines the amount that you can absorb. Okay, so basically it really depends on what is the vapor pressure of the VOC gas, VOC species in the gas phase, right? And if you have the liquid, then you can determine what is the mole fraction, or how much amount of the VOC you can absorb. So there's a second part of the problem is asking what is the mole fraction of the hydrogen sulfide in water that is in contact with the air, contains the hydrogen sulfide at a partial pressure of 0.05. So this problem is trying to convert the partial pressure into the mole fraction, right? So we have this Henry's law in here, right? So it's asking for what is the mole fraction. So the pressure divided by HA, right? It's asking for what is the mole fraction, this XA here. So we already know that the partial pressure is 0.05 atmosphere, right? We just need to find out what is the HA for hydrogen sulfide. So this is at 20 Celsius again, right? And we're looking at this column, hydrogen sulfide. All right, so this Henry's constant is going to be 0.0483. And remember, we have to multiply that by 10 to the 4th atmosphere per mole fraction. Okay, so if you plug in the values here, you can find that this is going to be 1.04 multiplied by 10 to the negative 4, which means that it's basically 104 ppm. All right, so to get the ppm value, you just multiply that by 10 to the 6, right, ppm. And you're going to have this final mole fraction of the hydrogen sulfide. Okay, so this is how we can use the absorption to remove the VOC. And as we show, we just need to apply this Henry's law, which is quite straightforward. And then we can determine what is basically what is the mole fraction of these VOC in the liquid. And also what is the partial pressure that's remaining in the gas phase, right? And we can go through this absorption and also like combustion method or other methods in our next class. Okay, so let me know if you have any questions. All right, so I hope that this calculation we showed earlier by using the condensation makes sense to you. Okay.